So welcome back. In this second video, we will continue discussing the semantics of propositional logic. So we'll go through a series of definitions, and I'm going to start with definition of words, models, and events. So a word is a state in which the value of each variable is null. We can take our example that we have been working in this lecture, the burglary example, where we have three variables: earthquake, burglary, and alarm. So we have 8 possible words in which each word has a different combinations of values true and false for each of the variables. So we have 8 possible combinations. So we have 2 elevated to the power of 3, then it will be 8, that shows all possible words in this setting. We can understand the word a little bit more formally as a function that maps each propositional variable, pi, into a value that belongs to the set true and false. We also call a word a true assignment, a variable assignment, or a variable instantiation. So we can look at a few examples here. For instance, burglary. Burglary is going to be true at the word W1. That is true. Okay, but it's also true in word W2, W5, and W6. Not burglary, it's true in the word W3. That is correct. And also, it's true that not burglary is true in the word W4, W7, and W8. And we can look at burglary or earthquake. So burglary or earthquake, let me just erase here. So burglary or earthquake, it is true in word W4. So that is correct, because true or false is true. So burglary or earthquake is going to be true in W4. That holds, right? But it also holds here in W1, because true or true is true. It also holds in W2. It also holds in W3, also holds in W5, and in W6. But it doesn't hold in W7 or W8 because we have a false and false for the two variables, both earthquake and burglary. So we can find this notation here to denote that a sentence of is true at the word W. So we saw in the previous slide that burglary was true at the word W1. So we can write W1, it satisfies or entails the sentence burglary. But things get a little bit more interesting when you start to define sets of words in which a sentence is true. So we call it the model of a sentence alpha, and we define it this way. So we call the model of alpha is defined as a set of words in which the word satisfies or entails the sentence alpha. And we have now a sort of a double definition for sentence. We're going to understand the sentence at the same time as the sequence of symbols that define the sentence. So remember from our previous video that we defined what would be a well-formed sentence, that will be that the conjunction, disjunction, and negation of variables in a well-formed way. We're going to also interpret the sentence as being the sentence, the set of words in which that sentence is true. And you may find that this a little bit confusing, right? So what is the sentence? It is the syntactical interpretation that we saw in the previous video, or this semantic interpretation that we are seeing now. And I will tell you that it's both. And even though it's a little bit confusing, we can think about logic like more or less a real language. So if we think in English, we have words. And a word is at the same time a sequence of letters, but also it has a meaning. So when we say a word to a person, that person will receive not just the the sequence of letters, but also the meaning of that word. So we will say something like, oh, a dog, right? And that person will understand the word dog, the sequence of letter, but also that we are talking about an animal. All right. And when in a real language, we say that we have synonyms, right? So we have like dog and canine, and these have the same meaning. When we define this set of words that we call the models of a sentence, we can also say that two sentences are equivalent. And we saw this in the previous video, right? So we saw that alpha, it implies in beta, it is equivalent to not alpha or beta, right? Why is that happening? It's because the set of words in which alpha implying beta is equal to the set of words in which not alpha or beta are true. So they represent the same set of words, so they have the same meaning, they are equivalent in a logical way. By the way, we're gonna use the terms sequence and events with the same meaning. They will at the same time represent the sequence of symbols and as well as the set of words in which the sentence is true. So if we interpret the sentence as its model, right, so the set of words in which the sentence is true, we can start defining some properties and some relationships between the sentences. So you're going to see in the future that we can define equivalence, that we can define implication based on this idea of the models of the sentences. We can also look at some properties. For instance, what are going to be the models of a conjunction of two sentences? And that is very easy to prove, but also very easy to understand in a more intuitive way, right? If we think that a conjunction of two sentences will only be true when the two sentences are true, so we can think that we'll have a set here for alpha and we have a set here for beta, and these are all the words that alpha is true, and this one is all the words that beta is true. And the words in which alpha and beta will be true will be the intersection between the two sets. And we can do something similar and think that, well, if we have a disjunction of two sentences, alpha and beta, so the words of this disjunction will be the union of the words of alpha and with the words of beta. And the same way we can think that, okay, we have a sentence alpha, and these are the words in which the sentence is true. And if we want to calculate what's going to be the words of not alpha, we can look at our universe set and say, well, it will be all the words in which alpha is not true. So we can define as the complement set of alpha. So we have here a very long list of examples just to check our understanding of these definitions of words and models. So let's come back to our example of the burglary, alarm, and earthquake, and let's see how it goes. So in this first example here is saying that earthquake is true at the words W1 to W4, and we can check here that it's actually true that earthquake holds for the words W1 to W4. Not earthquake is going to be true at the words W5 to W8, and that is also correct, right? If we invert earthquake, it's going to be true on these words here, W5, W6, W7, and W8. All right, so let's look at this example here. Not burglary is true at the words W3, W4, W7, and W8. So not burglary, it's true at the words W3, W4, W7, and W8. That's correct. Alarm is true at the words W1, W3, W4, W5, and W7. So alarm is true for W1, W3, W5 and W7. That's correct. So a little bit more complicated now. And asking about not earthquake or burglary. It's going to be true for W7 and W8. So let me just erase this. Otherwise, it's going to be a little bit too confusing. And we say, okay, earthquake. Earthquake is true for these words. Burglary is true for these words. If we take these two together, right? So it's going to be true for all these words here, right? But we are interested in the negation. So for the negation, what is remaining is the words W7 and W8. All right, so check. Let me erase these again and look at the next example. So, the negation of, the negation of earthquake or burglary or alarm. Okay, so it's going to be negation of earthquake or burglary. Now, or alarm. So we know that for the negation of earthquake and burglary, we have these two words that will hold in this first part of the sentence. And now we need to look at alarm, right? And we know that alarm is true for W1, W3, and W5. So at the end, we will have W1, check, W3, check, W5, check, and W7 and W8. All right, that's correct. The next example is earthquake or burglary implies an alarm. Okay, we don't need to do anything here because now we know that this sentence here that we saw in the previous example is equivalent to this sentence here. So we can check and build the truth table, but we don't need to do that because we know now that they are both equivalent. So if it's true that not earthquake or burglary or alarm holds for these words, so it's also going to hold for the words W1, W3, W5, W7, and W8. So it seems correct. All right, and the last example is not burglary and burglary is not true for any word, right? So that is true, we know that. So if you look at what is burglary here, is going to be true for these words, and not burglary is going to be true for these words. But when we look at the conjunction and compute the intersection between these two sets, it's going to be the empty set. So it's also correct. Okay, here we have two more definitions. One, if a sentence is consistent, and the other one if a sentence is valid. So let's start with the consistency. So we say that a sentence of is consistent if and only if there is at least one word W in which alpha is true, right? In other words, we are saying that if you look at the models of the sentence alpha, it will not be the empty set because there will be at least one word in this set. We say that if a sentence is not consistent, so it will be called inconsistent. So this is definition here. And a sentence of that is inconsistent means that the models for the sentence is the empty set. It doesn't hold for any possible word. We use the terms satisfiable as a synonym to consistent and unsatisfiable as a synonym to inconsistent, and we use the symbol false to denote that a sentence is unsatisfiable or inconsistent. So we are overloading the symbol false. It will be two different meanings to us. One is the original meaning that we have been using before, and now also to denote that a sentence is unsatisfiable or inconsistent. And the second definition is if a sentence is valid. And I'm going to say that a sentence alpha is valid if, sorry, there is a typo here, and only if it is true at every word. So in other words, we're saying that the models for the sentence alpha is the omega set, the set of all possible words. If a sentence alpha is not valid, we can identify at least one word in which alpha is false. That's okay. And we're going to use the symbol true to denote that a sentence is valid. So again, we are overloading the symbols. True has two different meanings. One is the original one that we have been using so far, and the second one is to denote that the sentence is valid. We also use this notation here to denote that the sentence is valid. So we can start define some logical relationships. And these logical relationships will involve two or more sentences. So we can start thinking about equivalence between sentences. So we can start comparing the meaning of the sentence and seeing how they related to each other. So there are four main definitions here. The first definition is two sentences, alpha and beta, are equivalent, and they will be equivalent if they are true for the same word. So we look at the models of alpha and the models of beta, and we see they are equal. So alpha is true exactly for the same words that beta is true. So we haven't seen this before. So we have it like alpha implying beta are going to be equivalent to not alpha or beta, right? And these two sentences are equivalent because they hold for the same words. And we haven't seen this before a few slides ago. We have two sentences, alpha and beta, being mutually exclusive if they are never true for the same words. So if you look at the sentence alpha and compute its models and compute the models for beta, and we take an intersection, it's going to be an empty set. So there is not a single word that holds for both sentences at the same time. Two sentences are exhaustive if each word satisfies at least one of the sentence. So in other words, if we take the union of the models of alpha and the models of beta, we get the omega set, right? So we can think like one sentence is covering part of the word, another sentence is covering another part of the word, but when I take the union, I have all possible words covered. The last definition here is implication, and we say that a sentence alpha implies in sentence beta if and only if beta is true whenever alpha is true. And we can interpret that as the models of alpha being a subset of the model of beta. We can also write that this symbol here, we can also use this notation here, saying that alpha implies or entails beta. And just to detail this idea a little bit more, right? So we can think of this is the set for the words of beta. This is the models for alpha. And when we have a word here inside alpha, it's going to be true for alpha. And because alpha is a subset of beta, it will also hold for beta. So whenever we have a word here that is true for alpha, it will also be true for beta. We are not saying anything for the words that are not true for alpha, right? So we may have something like here. It's possible. So in this case, it's true for beta, but not true for alpha. And we can have a word here that is false for both of them. This is also valid. But what we are saying is that implication means that whenever it holds for alpha, it should also hold for beta. So here we have a definition of several equivalences, and equivalents are useful when are working with propositional logic because we can derive some new sentence from existing sentences in a very simple way, just manipulating the symbols. And we have here what we call schemas, and the schema is in a certain way is a more general definition of a sentence. We can instantiate one schema to different sentence. What I'm trying to tell you is that if we have one sentence, one schema like alpha implies in beta, we can instantiate to different sentence For instance, this one, not A implies in B or not C. In this case, alpha will be not A, and B or not C is going to be our beta. So let's take a look on all those equivalences and check to see if they make sense. So some of them are really trivial, and we don't need to go into much detail to understand that. For instance, not true is equivalent to false. Okay, we can accept that, and not false being equivalent to true. Okay, it also makes sense. And false and beta is going to be false, because it doesn't matter what is the value of beta. We are making a conjunction with false, is going to be false. And alpha and true is going to be alpha. It makes sense because it will depend on the value of alpha to get the final result. So yeah, it makes sense. False or beta is going to be beta, okay? And alpha or true is going to be true. All right, so these are very simple ones. The next ones have names, so it should be a little bit more interesting. So double negation, not alpha is equivalent to alpha. It makes sense. Not alpha and beta, wow, that's interesting, is equivalent to not alpha or not beta, right? So this we call De Morgan, and these are very famous equivalents. So we use this a lot when we are deducting some new sentence from the existing ones. The second De Morgan equivalence is not alpha or beta is equivalent to not alpha and beta. Okay, the next two are known as distribution, and we can think as distributing here the alpha between this part of the sentence. So we have alpha or and beta and gamma, and it's like in doing alpha or beta and alpha or gamma. And the equivalent here, we have alpha and beta or gamma being equivalent to alpha and beta or alpha and gamma. Okay, we have also what we call the contraposition. So alpha implying beta is equivalent to not beta implying not alpha. And we haven't used this before, I guess, in some previous slides. And we have the definition of equivalence and the definition, of implication and equivalence. So if alpha implies in beta, it is equivalent to not alpha or beta. And alpha being equivalent to beta is equivalent to alpha implying beta and beta implying in alpha. Okay, and these are some reductions. It's basically showing some equivalence between relationships and the properties of satisfiability and validity. So I will not go through this in all the details, but some of them are quite obvious. For instance, if we look at here and we have alpha and beta are mutually exclusive, it means that alpha and beta are is unsatisfiable. So well, okay, that we can accept that, right? So we have like alpha and we have like beta here. They are mutually exclusive, so the intersection between them is an empty set. And if you look at what is going to be alpha and beta, it should be unsatisfiable, right? So because there is no intersection here, so alpha and beta will never hold. There is not a single word where alpha and beta, the sentence alpha and beta is true. So maybe a little bit more difficult to see is the first one. We say alpha implies in beta means that alpha and not beta is unsatisfiable. We can think a little bit about this, right? So we have like alpha, we have beta, and we have alpha implying in beta. So we know that it's going to be true for this case, it's going to be false for this case, and true for this, and true for this. And we can also define not beta. In this case, not beta is going to be 0, 1, 0, 1. And finally, we can define alpha and not beta. And alpha and not beta. So we are looking at this and these columns, and it's going to be 0 here, 1 here, and it's going to be 0 here and 0 here. So basically we're saying that if alpha implies beta, so alpha implies beta is true for these words here. But when we look at alpha and not beta, for these same words, let's call it W1, W2, W3, and W4, for the same words, this expression, this sentence, alpha and not beta, is unsatisfiable because it is never true. So for the word W1, it's false, for the word W3 is false, and for the word W4 is also false. Alright, so we haven't seen several definitions. I'm assuming now that you are tired. I am tired too. It's a good moment for stretching our legs, grabbing a coffee, and taking a break. So we will continue in the third and final video, where we're going to discuss the idea of monotonicity of propositional logic using the definitions that we haven't seen so far. So see you soon in the next video. Bye.